Hello, good morning, sir.
Hello, madam. Good morning. Are you able to hear me?
Sir, somewhat voice is low, sir.
Hello, madam.
Sir,
Ye-
okay now.
Okay. Okay.
Okay. Sir, shall we start the session, sir?
Yes, madam.
Okay, thank you, sir.
Thank you.
Honorable Chief Guest, respected Chairman, Principal, faculty, and research scholars from various institutions, and at last, all my dear students. Good morning to everyone present here today. I welcome all of you for this last day of 1 week faculty development program on strength of durability characteristics bacterial cement mortar, which is jointly organized by Department of Civil and Mechanical Engineering. It is a glorious moment to extend my warm wishes on behalf of the Department of Civil and Mechanical Engineering from Sanskrithi School of Engineering, Puttaparthi, to our Honorable Chief Guest, Dr. V Senthil Kumar, sir. I want to convey my heartfelt gratitude to you for accepting the invitation and presiding over this event. I would like to give a warm welcome to everyone who is attending the 1 week faculty development program. With great pleasure, I introduce our distinguished guest, Dr. V Senthil Kumar, sir, Professor and Head, Department of Civil Engineering, Kumaragaru College of Engineering, who is present here to deliver the content of strength and durability characteristics of bacterial cement. Sir got the first class in his bachelor degree in civil engineering from IRTT Institute of Road and Transport Technology under Bhartiyar University, Coimbatore. He has graduated a master degree in environmental engineering in Government College of Technology, Coimbatore under Anna University. He obtained his doctorate in Anna University, Coimbatore. He has got 16 years of teaching experience and around 3 years of industry experience. He has published in many international journals in Scoopers and etc. Sir, total 8 faculty members was registered PhD under his guidance. And also he has filed total 8 patents and also is a journal reviewer for Journal of Advances in Civil Engineering from 2015 to till date. He given many special lectures and also contributed as a chief guest in national level conference in JKK Muniraj College of Technology in 2018. Sir, first of all, I welcome you for this session, sir, and also we are very grateful to you for accepting our invitation. Welcome you, sir.
Thank you, madam. A nice introduction to me. Uh, Good morning to all and all gathered here. Madam, are you able to hear me, my voice?
Yeah. Yes, sir.
Okay, madam. Okay. Good morning to all and all gathered here. First of all, I would like to thank you. This faculty development program on recent trend in material technology, organizing team, coordinators, and head of the department, Dr. A.S. Ramya, and Sanskrithi School of Engineering and Management for giving this opportunity for me. One minute, I will share my screen.
TCS. Oh, I stopped sharing the.
are you able to see my screen? Hello, madam. Ma'am?
Yes, sir. It's visible on.
Okay. Good morning, professors. My topic is experimental studies on strength and durability characteristics of cement mortar embedded with bacterial species. All of you know about cement mortar. Cement mortar is nothing but the mixture of cement and sand combined with water. That is called cement mortar. All of you know. How to improve the compressive strength as well as durability properties of this cement mortar means we introduce some bacteria during mixing and curing process. Then that bacteria produces urease. That urease finally converted into calcium carbonate. That calcium carbonate fill the voids in between the cement sand matrix, so automatically increase the compressive strength as well as durability properties of the cement mortar. Next, we move to introduction part. Are you able to see my screen?
Yes, sir. It is visible, sir.
Okay, sir. Mortar is a workable paste used to bind the construction material to fill the voids in between them. Then it becomes hard when it sets, resulting in a rigid concrete structures. Cement mortar is a combination of hydrated cement and fine aggregate. Day by day, usage of cement mortar or concrete is increased. Next to the water, the most used commodities of people is this concrete. Then modern mortars are typically made up of mixture of sand, cement or lime. And the cement or lime act as a binding material. It is combined with the water. The addition of bacteria in modern mortars produces bacterial or microbiologically induced carbonate mineralization. That is called MICP. Introduction of bacteria into the cement mortar. This bacteria produce microbially induced carbonate mineralization, that is called MICP. Sir, my slide is changed or sir, actually I go to third slide.
No,
sir,
sir.
it
It's
is.
not changing.
Not changing.
Mhm.
1 minute.
Now it's changed, sir.
Okay.
Okay, sir.
Sir, the entire screen எப்படி பண்றது actually? Okay. இது full screen. இல்லை சார் பிபிடிவே சார் பண்ணலாம். ஆமாம் பிபிடி நான் ப்ரெசென்ட் பண்ணுறேன். பிபிடி இங்கே இருக்கு. இது ஃபுல் ஸ்க்ரீன் வச்சுக்கணுமா? இல்லை சார் இன்னும் ஷேரே பண்ணல. இல்லை சார் இது இதுக்கு வர்றது எப்படி?
இதில் வந்து ஷேர் செய்யுங்க இந்த ஆப்ஷன்ஸ்.
ஓகே.
அது
எந்த
ஸ்க்ரீனே பண்ண போகிறேன்.
ஆமாங்க.
அப்போ அது
ஆனால் இங்கே வர மாட்டேங்குது.
என்ன பண்ண சொல்லுங்க
சார் அந்த பிபிடி வரணும் இல்லை?
அது கொடுக்கலாம் சார், கொடுங்க. ஷேர் கொடுத்துட்டு நீங்கள் வந்துடும் சார்.
ஓ, ஷேர் கொடுத்துட்டு இங்கே வந்து
நீங்கள் என்ன இருந்தால் அப்படியே தெரியும் சார்.
அப்படியா? பார்க்கலீங்க, நானும் தான் கனெக்ட் ஆயிருந்தேன். இதில் பார்க்கல
ஷேர் கொடுக்கல சார். ஷேர் கொடுப்பீங்க. ஷேர் கொடுக்கலாம்.
சார் இதா?
ஷேர் கொடுங்க சார்.
சார் இது எனேபிள் ஆக மாட்டேங்குது. இதே ஸ்கிரீன். ஓகே, இப்போ இதுக்கு வந்துடலாம்.
equals to
FI கொடுத்துடலாம்.
F5. Shift பண்ணிட்டீங்கன்னா அந்த பேஜுக்கு வரும் சார். இப்போ என்ன பிரச்சனை சொல்லுங்க. Shift பண்ணிட்டீங்கன்னா அந்த பேஜுக்கு தான்.
இப்போ இது ஃபுல்லாக கொடுத்துடலாமா? எப்போ மாதிரி hello madam, now
sir, now it's
okay
coming.
okay madam. So the bacteria is added into the cement mortar. It produces microbially induced carbonate mineralization. It is called the MICP. Then this MICP is called in different name. First one is microbially induced, bacterially induced, microbiologically induced calcium carbonate precipitation, microbiologically mediated mineral precipitation, biocementation, microbial cementation, biodeposition, biocalcification, microbial plucking process, and the biomineralization. Extra, right? The bacteria is introduced in cement mortar. It produces MICP. This MICP is called in different way. It has been proposed as a novel and environmental friendly strategy for the production of cement mortar and concrete. Then what is called bacteria embedded cement mortar means ordinary cement mortar we know. The mixture of cement sand with the water is called cement mortar. Then in addition to cement mortar, we added some bacteria into the this cement mortar through mixing process as well as curing process. So these bacteria produce carbonate. That cement mortar is called bacteria embedded cement mortar. The bacteria produce some calcium carbonate. That calcium carbonate fill the voids between the cement and sand matrix. So automatically strength and durability characteristics of the cement mortar will increase. Bacteria can continuously create a resistant calcite layer over the surface which is insoluble in water. Bacteria act as a self-healing agent that produce up to 100 micrometer sized calcite particle on the surface of the cement mortar. It is an important area of research for high performance construction material. Then we move to material method and instrumentation. Material nothing but cement and sand. First, Portland Pozzolana cement with the brand name is ACC was used in this study. It confirms IS 1489-1991 with the specific gravity of 3.1. The photo view shows the ACC cement. Then next material is sand. Locally available clean river sand conforming to IS 650-1991 with the specific gravity of 2.7 and the fineness modulus of 2.96 is used as a fine aggregate. Here I have used 3 types of sand. It confirms N-wood sand conformation. That means the sand is passed through 2.36 mmC and retained in 1.18. Then 1.18 passed 700 micron retained sand. Then 700 micron passed 90 micron retained sand. 3 variety of sand. This is coarse, medium, fine sand. These 3 type of sand is used in this project. Then it is used as a fine aggregate. Then these are the bacteria I have used in this research. Actually, Enterobacter, designated as FY973549. This is denoted as EB1. Then Enterobacter 2, this designation as FJ973550. Then Enterococcus and Serratia. This FJ and the numerical value denotes the bacteria designation. Right? This photo view shows the Enterobacter, Enterococcus, and the Serratia photo views. Then my experimental investigation is divided into 2 parts. First part is mechanical properties. Mechanical properties nothing but compressive strength and tensile strength. Then durability characteristics, I have performed the following tests. First one is water sorptivity, then water absorption, acid attack, and a rapid chloride penetration test. These 4 tests I have done. And this is the specimen. uh, I have done totally 663 specimen. For mechanical properties, I have done compressive strength and tensile strength. For durability, I have performed 4 tests. Totally 663 specimen is used in this study. In addition to that, these two are B4 prop medium and bacterial culture grown solution. These two solution is very much important. For initial growth of bacteria, I have used B4 prop medium. It nothing but 0.5% yeast extract and 0.5% glucose and 1% calcium acetate. This solution is soaked at 30 degrees centigrade for 3 days to multiply the bacterial species. This is initial stage. After growed bacteria is mixed with this bacterial culture grown solution. This is nothing but a combination of 8 gram nutrient broth and 2% urea. In addition to that, these two are common. 8 gram nutrient broth and 2% urea is common. Then I have changed this 4 calcium sources. First one is 25 millimole of calcium hydroxide, then 25 millimole of calcium acetate, then calcium chloride and calcium oxide. This first two chemical component is common. Third one is I have changed. Totally, I have prepared 4 combination of bacterial culture grown solution. Then casting and the preparation of cement mortar specimen. Actually, B4 prop medium consists of growed bacteria. That growed bacteria contains 3 ml. 3 ml of B4 prop medium contained different bacteria is added in different calcium source. I have prepared 4 calcium source. That 4 calcium source is stored in separate container. After that, this well-growed bacteria is mixed with this 4 type of different calcium sources. And this solution is used for mixing as well as curing process of the cement mortar cube. This is the process of mixing. Here, a mixing process is done. Then this is the casting process. I have used a cement mortar specimen for this study. Then after the demolding, this bacterial cement mortar specimen is cured in this bacterial culture grown solution. This is the curing process. This slide shows the curing process of the cement mortar specimen. In this study, I have used the following instrument. First one is a computerized universal testing machine. All of you know about the computerized universal testing machine. This machine is used to find the compressive and tensile strength of the concrete as well as cement mortar. Then lambda 35 UV visible spectrometer is used to find the optical density of the prop medium. Then optical tracker is used to probe the microorganism. Then scanning electron microscope is used to analyze the microstructure of the specimen. Then XRD is used to analyze the presence of calcium carbonate in the cement mortar specimen. And the entire work is divided into 2 phases. First phase is visual observation. That means I have measured only pH value of the bacterial culture grown solution. Then microstructure analysis and testing. Second phase is microstructure analysis and testing. Here I have done SEM and XRD, compressive strength, tensile strength, water sorptivity, water absorption, acid attack, RCPT test. The first test is pH measurement. This is the first slide shows the grown bacteria in B4 prop medium. Then mixing of grown bacteria in different calcium sources. Second slide shows the mixing process. After mixing, the next after 24 hours, after mixing the B4 prop media of bacteria, after 24 hours, we have observed some white deposit on this rod rib, right? So this is the calcium carbonate. After that, I have measured the pH measurement. Actually, bacteria mixed calcium source shows higher pH value as compared to normal solution. This is the observation. No pH value variation in PCGS1, right? The pH variation is constant in the absence of the bacteria solution. Increasing pH value in bacteria contained PCGS1, that means 8 gram nutrient broth, 2% urea, and 25 millimole of calcium hydroxide solution shows high pH value due to the enrichment activity of biochemical reaction by the bacteria in PCGS1. A higher pH value is noticed between PCGS contains without bacteria and other PCGS2, S3, and S4. Poor activity of bacteria with other calcium source, it shows a small variation of pH compared to PCGS1, which in turn reduce the calcium carbonate precipitation. Different calcium source. Actually, first slide shows variation of pH in Enterobacter 1 with the time at a different calcium source. Here, the Enterobacter 1 is mixed with the 4 calcium source. What is the pH range? Is observed in this figure. Then Enterobacter 2 is mixed with a different calcium source. What is the pH value? Third and fourth, likewise, third and fourth, Enterococcus and Serratia bacteria is mixed with a different calcium source. What is the variation of pH is presented in this slide. Then we move to XRD. XRD is used to analyze the presence of calcium carbonate. The scanning sample by the 2 theta value is 5 to 90 degree. Induced crystallization characteristics peaks are noticed such as vetrite, argonite, calcite of calcium carbonate at 2 theta value around 26, 27, 28, 36 degree, 39, 42, 49, and 50. Degree. The bacteria embedded cement mortar specimen shows high intensity peaks. That means vetrite 2 theta value is 6 degree, 27 degree, 27 degree. Actually, these bacteria produce calcium carbonate. This calcium carbonate presents in the following form. That means vetrite, calcite, and argonite. These calcite, vetrite, argonite are observed in XRD pattern. In the control specimen, this values corresponding to vetrite, calcite, and argonite. This is the other specimen. The first slide shows the XRD diffraction pattern of Enterobacter embedded cement mortar species. Here, a control specimen shows less peak of 2 theta value, around 500. Here, this EP1, PCGS1 contained specimen shows higher peak value of 2 theta value, nearly 2500. Likewise, XRD diffraction pattern for EP2 embedded cement mortar specimen and also ECP embedded cement mortar specimen and Serratia mixed cement mortar specimen. This theta value shows vetrite is observed in 50 degree, calcite is observed in 36.7 degree, argonite is observed in 26.8 and 27.3 degree, 3 degree. Next, we move to SEM image. This first slide shows the control specimen SEM image. Then second photo shows the Enterobacter embedded cement mortar specimens SEM image. Here, these are the observation. MICP in the sample are examined through SEM. There is none of evidence is observed for the calcium carbonate precipitation in the control specimen. In control specimen, there is no calcium carbonate. Here, there is no white deposit is observed, but in the dense formation of the MICP is identified in the microbial cement mortar specimen. The second photo shows the dense formation of white deposit. It is called calcium carbonate. Then bacterial, because of the significant bacterial activity, a clear deposition of white calcium carbonate precipitation is identified in the biocuring cement mortar specimen. This MICP is the one of the substantial for increasing compressive strength in the bacteria-treated cement mortar specimen. So next slide shows the some of the same image of bacteria mixed cement mortar specimens. This is the EB2 mixed cement mortar specimen same image. This is Enterococcus embedded cement mortar specimen same image. From this slide, the white calcium carbonate deposition is gradually decreased. And this is the compressive strength test and the failure pattern. Load is applied as per IS code. And this is the compressive strength value tabulation and graph. Actually, Enterobacter embedded with the PCG-S1 shows 28 days compressive strength is 54. This is the control specimen, 28 days strength is 37.3. Nearly 50% of value is increased due to the addition of bacteria in cement mortar specimen. This is the split tensile strength testing apparatus. Load is applied as per IS code. EB1 embedded cement mortar specimen shows 12% increment in split tensile strength due to the significant activity of the bacterial species in the PCG-S1 specimen. The formation of MICB in between the cement sand matrix, which in turn increase the load resisting capacity of the specimen. This is the split tensile strength test value and the corresponding figure. Next we move to durability test. For durability test, first test is sorbidity test. Sorbidity is one of the parameters to affect the durability of the concrete structure. The rainwater will enter into the structure through capillary pores present in this structure. The rising water table in the foundation, water may enter into the wall due to capillary pores. So this is the test apparatus of sorbidity test. Here I have used 50 mm diameter and 100 mm height cylindrical specimen, casted and cured for 28 days. After 28 days, it is tried at 100 degree centigrade in a ventilated oven. Specimen were coated with waterproof resin of ISO 0081 except the top and bottom of the cylindrical specimen to ensure the unidirectional absorption of water. Then specimen was submerged up to 5 mm height water. The specimen were removed from the water and waited after drying the surface with a towel every 15-30 minutes. 1.5, 3, 5, 8, 24, 72, 96, 120, 144 and 168 hours. Immediately after each measurement, the test specimen were sunk again into the water. The sorptive coefficient K was observed by using this above equation. Q by A equal to K root T. From this observation, this is the sorptivity coefficient of cement mortar specimen. This is the EB1 PCG-S1 mixed cement mortar specimen. Sorptivity coefficient is 0.00267. This is the very low value. Compared to this value, higher other specimen shows some of the higher sorptivity coefficient. And this is the water absorption versus time in control specimen and EB1 embedded cement mortar specimen. Likewise, EB2 and ECB and Serratia mixed specimens sorptivity coefficient. The black color shows control specimen. Control specimen sorbidity coefficient very high as compared to this one, EB1 PCGS1. EB1 PCGS1 is denoted in bottom red color. This is the very low coefficient as compared to control specimen. Likewise, this EB2 mixed specimens sorbidity coefficient is very low as compared to control specimen. From this observation, this is the conclusion we have derived. The first one is a drastic water infiltration was noticed in control specimen. Then 13 times reduced capillary water absorption was noticed in the bacteria treated PCG S1 somatological specimen. Then this is mainly due to the tensor interfacial zone formation of calcic precipitation between the cement and sand matrix. In biocuring process, microorganism shows good growth condition at calcium hydroxide microenvironment. It produces urease to hydrolyze the enzyme urea fully so that the calcite layer is finally precipitated in gradual manner. This is the chemical formula of formation of calcium carbonate. Actually, the bacteria produce urease. This urease is combined with atmospheric carbon dioxide. Finally, it converted into calcium carbonate, CaCO3. This is the chemical equation involved in this process. Next, we move to water absorption. For water absorption, I have prepared a cement mortar cube of size 70.6 mm into 70.6 mm into 70.6 mm. This test was done as per ASTM C64297. Then the specimen were dried 105 degrees centigrade for 48 hours. Then the initial weight is measured. That initial weight is denoted by W1. Then the specimen kept immersed in water continuously for 48 hours. After the 48 hours, again we measure the final weight. That is denoted by W2. Then this is the equation to find the water absorption percentage. W2, final weight minus initial weight divided by initial weight in the 100 gives water absorption of the given specimen. Then this slide shows the water absorption in control as well as microbial cement mortar specimen. Actually, first one is the Enterobacter combined with the PCGS1. Specimen shows less water absorption as compared to control specimen. This EB1 specimen shows 1.22% water absorption percentage, but control specimen shows 3.01%. Likewise, the other bacteria water absorption is presented in this slide. This is second slide shows the EB2 embedded cement mortar specimen. Third bar chart shows the ECB embedded cement mortar specimen. Fourth bar chart shows the Serratia embedded cement mortar specimen. Then acid attack on bacteria embedded cement mortar specimen. For that purpose, I have used a cement mortar specimen. The mixing and the preparation procedure were made accordance with IS 4031 Part 6 2000 by following the test procedure of the author Reddy et al. The test procedure I have followed Reddy. Acid attack experiment was carried out, analyze the weight loss percentage. Then the specimen were tried after 28 days. The specimen were tried at 105 degrees centigrade and the initial weight was measured. The initial weight is W1. Then the test specimen were kept in solution for, this is the ratio, HCl is 1 and H2SO4 is 1:1 ratio. I have prepared the solution. Then this initial weighted specimen is immersed into this acid solution for 28 days. After 28 days, the specimen were tried at 100 degrees centigrade. The loss of weight of specimen was measured. That measurement is W2. EB1 embedded PCG-S1 specimen shows less weight loss in acid medium as compared to other specimen. MICB in the microbial cement matter act as a resistive surface area to hazardous material infiltration, deterioration of the cement matter surface is reduced. Actually, this MICP prevent the penetration of acid into the cement matter specimen. This is the formula I have used to find the acid attack. W2 minus W1 divided by W1 into 100. Then this is the appearance of controlled specimen in the acid attack. Second slide shows the second photo shows the EB1 embedded cement matter specimen, right? EB1 embedded cement matter specimen in the acid attack. Here in this surface, so many surfaces are attacked by acid. Here, not like that. The deterioration is very less as compared to control specimen. This is the weight loss percentage of MICP specimen. The first one, EB1 PCG-S1 embedded cement matter specimen shows 7.83%, but the control specimen shows 13.32% weight loss. As compared to control, bacterial embedded cement matter specimen shows less weight loss. Likewise, EB2 embedded cement matter specimen and ECP embedded cement matter specimen and Serratia embedded cement matter specimen weight loss is shown in this figure. Next test is rapid chloride permeability test. For the purpose, I have made a specimen. Diameter is 50, 100 mm diameter and 200 mm length. This cylindrical specimen is cut into 3 pieces. The piece size is 100 mm dia and 50 mm length. This is the experimental setup. Actually, this is the specimen. One side of the specimen, we used 0.3 normality NaOH. It is connected to positive terminal. Then next end is embedded with 3% NaCl. This end is connected with the negative terminal of the voltage meter. And the constant 60 volt is passed through this specimen. The permeability classes for different microbial specimen was calculated. Then the result is compared with the standard value of permeability class to understand the chloride ion penetration to the cement matter specimen. From this test, we have concluded that due to the presence of pores and voids, the control specimen permit the flow charge of around 1766 coulombs. But the specimen embedded with the EB1, EB2, ECB and Serratia with PCG-S1 permit 397, 436, 455 and 467 coulombs respectively. As compared to control, this value is very less. This is mainly due to the formation of MICP in the pores and voids which resist the flow charge. So this table shows the average charge passed in control as well as the MICP specimen. EB1, PCG, S1, S2, S3, S4 specimen shows less charge flows as compared to control. Likewise, this EB2, PCG, S1, S2, S3, S4 shows higher value as compared to EB1. Likewise, ECB and Serratia flow charges is denoted in this table. This shows the current time relationship at a constant 60 volt control specimen. Likewise, this is EB1 mixed specimen, second one is EP2 mixed specimen, third one is ECP mixed specimen, and last one is Serratia mixed specimen. Relationship between current and time at constant 60 volt. Next, we move to conclusion. From this study, we have concluded the following point. A noteworthy of present work is used to erase producing bacteria such as Enterobacter, Enterococcus species source, enhanced composition up to 44% and considerably reduce the water infiltration in the specimen. Also, enhanced split tensile strength is noticed in the bacteria treated microbial cement mortar. The improved durability through biocalcification in the cement mortar specimen is evolved by measuring water absorption and rapid chloride ion penetration test. The first time in civil history, 13 times reduction of water absorption has been successfully achieved in the Enterobacter species embedded cement mortar specimen. From RCP test, the reduction in charge value indicates the better resistance to chloride ion penetration and lower permeability to the microbial cement mortars. This microbial technique will provide the basis for the alternative high quality cement mortar specimen sealant. It is environmentally safe and eventually will enhance the strength and durability properties of the building material. And this methodology is used in the following application. The microbial cementation would be used for the civil and environmental engineering application. First one is to enhance the stability of the retaining wall and to improve the strength of embankment and dams, to reinforce underground construction, to construct a permeable reactive barrier in mining as well as environmental engineering, to increase the resistance to petroleum borehole degradation during drilling and extraction process, to control the erosion in coastal areas and rivers. It is also used in piled and non-piled foundation for treating pavement surfaces. This is the sum of the reference I have used in this work. Actually, we know about cement mortar. Cement mortar is nothing but the mixture of cement and sand mixed with some water, right? How to improve the compressive strength or durability properties of the cement mortar means actually we induce some of the bacteria. That bacteria produce urease. Urease is combined with atmospheric carbon, atmospheric CO2. Combined with the urease, combined with atmospheric CO2, it react and finally it produces the calcium carbonate, right? This calcium carbonate is fill the voids present in the cement mortar as well as concrete. So automatically increase its mechanical properties as well as the durability properties of the cement mortar. This is the main concept is presented in this study. Okay, actually we identify the urease producing bacteria. That bacteria produce urease. That urease is reactive with atmospheric CO2. Then finally it produces the calcium carbonate. That calcium carbonate is fill the voids between the cement sand matrix, or automatically our mechanical properties as well as durability properties of the cement mortar specimen is increased. Actually, the formation of calcium carbonate is identified from two tests. One is SEM test. In SEM test, we observed that some of the white deposit is there, right? So, as per literature, this is identified as a calcium carbonate, right? And also, SEM test it confirmed the some white deposit. So this is the calcium carbonate. This calcium carbonate is confirmed with the XRD test. XRD produce 2 theta value. That 2 theta value is correspond to laterite, aragonite, and calcite. So calcium carbonate is present in 3 forms: laterite, aragonite, and calcite. From this 2 microstructure analysis, I have concluded that the white deposit has a calcium carbonate. Any queries? Hello, ma'am. Dear participants, you have any query, please ask me.
Hello.
Tell me, sir.
No. I'm asking for the audience. Are there any questions from the audience side? No questions in the chat box also. So we assume that there are no more questions. So we are moving on to the valedictory session of the FDP. Good morning, everyone who are here gathered for a purpose. I thank B. Vijay Bhaskar Reddy Garu, the chairman of Sanskrithi Group of Institutions, the principal Dr. A. Senthil Kumar, HODs of various departments, and various coordinators who have served to make this function a grand success. Now we have arrived at the last phase of the faculty development program on recent trends in materials technology. This FDP encompassed various aspects of materials like manufacturing aspects, design aspects, and implementation part of the materials under consideration, no matter whether civil engineering uses or the mechanical engineering. We have decided to conduct FDP jointly. The main problem was to fix the topic itself. So as you all agree with me that R&D in materials is nowhere restricted to any branch of engineering. Only the application part may differ because of its domain needs. Objective of this FDP was to share the knowledge of materials from various points of view, both from commercial aspects as well as R&D aspect. The sessions were well organized and well managed by the resource persons of reputed institutions, the response to which in the form of feedback was overwhelming. Before I proceed, I would like to hand over the mic to the audience to give us any suggestions or feedback on the organizations or about responses which will be treated as a guidance.
Sir, good morning.
Good morning.
Hello. Am I audible, sir?
Yeah, you're audible.
Sir, myself, Dr. Ashish Urade from Ramdev Baba Engineering College, Nagpur, Maharashtra. Hello.
Yes, sir. You're audible.
Sir, FDP was very nice, nicely organized in terms of the time duration and all these things. We were very convenient regarding the tenure of the time. Though it was a blend of civil and mechanical engineering, as I belongs to the mechanical fraternity. So the topic in civil engineering, which might be we are hearing for the first time. So it was very nice sessions. Thank you to the organizing team.
Thank you, Ashish sir. Anybody else from the audience? Okay, continuing upon, this FDP could not have been a possibility without a wide network, without participants. We are thankful to the teaching fraternity who have shown interest in the participation of this FDP. We have had around 250 registrations, and every day we have received feedbacks on an average 120 plus throughout the week. Thank you so much for your support, and we expect similar kind of response in future also. Now I would like to thank our resource persons, Dr. M. Srinivas Reddy, Professor and Principal, RL Jalapa Institute of Technology. He has delivered his lecture on role of materials in engineering, an overview. Role of materials in engineering, an overview. He delivered it on 25th. And next resource person was Dr. V Senthil Kumar, Assistant Professor, Department of Civil Engineering, Kongu Engineering College, Erode, Tamil Nadu. And his topic was development of agro-based biomass briquettes from sorghum pinnacle and pearl millet. Then came a software-related talk by Mr. Vivek, which was co-hosted by Dr. Harish Lambadi. Mr. Vivek is the Business Development Manager for the Asia Pacific region from Hexagon MSc, Master and Software Engineer. And the topic he delivered was on multi-scale modeling and material with a Digimat. Then the session was followed by Dr. G.L. Satyamurthy, Professor Civil Engineering, Kumaraguru College of Technology, and the topic of delivery was composite materials and its application in engineering. This session was followed by Mr. Shekhar Dikshit, Rishi Tech, Bangalore, and the materials, challenges and opportunities. And today's resource person was Dr. V Senthil Kumar, Professor and Head, Department of Civil Engineering, M.Kumarasamy College of Engineering. And the topic was strength and durability characteristics of bacterial cement mortar. So thank you one and all who have put in your efforts as well as you have spared your time for this FDP program. Thank you one and all once again. Thank you. Good day.